So good morning or good afternoon or good evening, in this case, good morning. So welcome to the episode number 62 of the Physics Matter Colloquium series. So I'm Christine Darve from the European Spallation Zone in Sweden and former chair of the Forum of International Physics at the American Physical Society, which proudly support this series. So today we are going live from the antipode of Europe and Australia, including America as well. And locally in Australia, this is 2 a.m. local time for our special guests. So very early morning. So joining me as well on this panel, so we have also Alan Hurd, who is from Los Alamos National Lab, and he's also a former FIP chair. So our series, Physics Matter, invite everyone curious about physics to share our world. So over the past 5 years, we have explored research infrastructure, discoveries, accelerator, and international collaboration. So in 2025, we traveled across Africa. We celebrated the International Year of Quantum, finishing in December with Ana Maria Seto, so in Mexico, and we connected physics to society in inspiring ways. So all the past episodes are available on our FIP channel and our webpage. So today, using the unique lens of neutron and photon, we are exploring how physics help uncovering and preserving cultural heritage. So our speaker, Dr. Joseph Bevitt, is a 3D imaging scientist and group manager at ENSO, which is the Australian Centre for Neutron Scattering. So he leads the imaging and strength scanning group, using neutron and synchrotron light to study fossil, important cultural objects, and also all those different advanced material. So Joseph earned his PhD in chemistry from the University of Sydney and has held a key role managing ANSTO research program. So he also served on advisory boards for different museums and cultural heritage and cultural center, both in Australia and internationally. And his discovery has been featured in Science, different exhibition, media outlet, and even on postage stamps and coins. So showing how science can bridge and can bring history to the culture and to life. So we are excited to start 2026 from this other side of the world with this fascinating journey that all of us, it recall our young age also, thinking and understanding what paleontology is. And this is a journey into the science of heritage. So thank you so much to bring your question on the question and answer a little box that you have at the end, or we can have you as well asking your question live at the end of the talk, which should be about 40 minutes. So Dr. Bevitt, so the floor or the screen is yours.
Thank you. Okay, am I sharing the right screen?
Yes, you do.
Excellent. Thank you, everybody, for your attention this morning, this evening, tonight, whatever time it is for you. So my name is Joseph Bevitt. And I'm here to present not just what our local achievements are in cultural heritage research, but also how I came to be introduced to this field in the first place and what our engagements with museums have resulted in terms of new capabilities for our facility and new directions for our research. So I work for the Australian Nuclear Science and Technology Organisation, which is a federal agency. We're a federal government agency, and we are capital rich. So we operate Australia's only nuclear research reactor, the Opal Research Reactor, and also the Australian synchrotron, which is the brightest light source in the Southern Hemisphere. The reactor is based in Sydney, and the synchrotron is in Melbourne in Victoria. We have a staff of around 1,400 people. We've been operating for about 60 years. In terms of our mission, we have 3 priority research areas that we support our nation, and that is in the environment, the nuclear fuel cycle, and human health. So we use our over 400 available nuclear methods to investigate these areas, but we also operate a user program, a merit-based user program for many of our facilities. So users from around the world can actually come to Australia or mail their sample to us, depending on the arrangement, to access our national research infrastructure. So that includes radiocarbon dating and other isotopic methods at our Centre for Accelerator Science. It includes the more than 15 beamlines now available at the Australian synchrotron. We have a national deuteration facility as well that enables new pharmaceutical developments and investigations that utilize neutrons, and also our multi-purpose reactor and the neutron activation, neutron scattering, and other techniques that are available there. So our reactor's been operating since 2007, so it's quite mature in terms of the research program deliverables at the moment. It is a multi-purpose research reactor. So it's a 20 megawatt reactor. It's relatively new. So that means it uses low enriched uranium. So it operates at blood temperature. So I keep getting questions, do we generate power from our reactor? And the simple answer is no. It's used to produce our national radioisotopes for medicine, high-end silicon ingots for semiconductors, and also provide neutrons for our neutron scattering labs. So ultimately, our reactor is a neutron factory. And if you don't know what a neutron is, it's a subatomic particle found in the nucleus of all atoms except for the ordinary hydrogen nucleus. We use those neutrons in our lab at the Australian Centre for Neutron Scattering. I mentioned we have 15 neutron beam instruments. This is an overhead view of our neutron guide hall, where there are about 3/4 of our instruments in that single room. We have around 450 researchers from around the world that come use this infrastructure. From my perspective, our neutron scattering lab is a one-stop shop. It means that users from around the world can use neutron methods to interact with atoms, either through transmission, absorption, or scattering, and using a host of techniques to look at materials non-destructively from a micro scale to a macro scale, or even an isotopic scale. So if you want to understand the structure, the bonding, the properties, or the potential applications for materials, they can be brought to our facility to investigate those in a hierarchical manner. The fun part is that our instruments are actually named after animals. And there's a benefit to us, because if someone publishes a paper with the word dingo, which is an Australian native dog, and the word neutron in a paper, it means that we can find the research outputs from our instruments fairly easily. But echidna represents our high-resolution neutron powder diffractometer. It produces spikes in the pattern, and it's a lot easier to say echidna than it is to say high-resolution neutron powder diffractometer. And given the thousands of students and high school students and junior students that come to our facility every year, this is their first introduction to our facility. And it's a nice way of creating, breaking the ice with visitors. Now, I operated a team of 2 instruments. The first one is DINGO, which is our thermal neutron radiography or tomography instrument. Dingo is the one and only Australian dog that's been in the country for about 5,000 years, so it's our native dog. And there's an image of Dingo there. We have a lean team. So there are 4 people in this photo. We're down to 3. So there's myself on the left-hand side with the beard. I'm the group manager. I took over from Ulf Garber, who was on the right-hand side. He was the prior group manager. He also designed and built the instrument, and is an absolute legend in his field. And Floriana in the white shirt there runs our Culture Heritage Research Program. Amongst us, the 3 of us, and Helen recently left, we operate our instrument around 300 days a year, of which 150 days is a merit-based user program. The rest is commercial and internal work. Our other instrument, Kowari. Kowari is a native marsupial that you can see there on the bottom left-hand side. Kowari is a residual stress instrument, and I haven't mentioned what DINGO does yet because most of this talk is going to be focused on it. But Kowari is really used for looking at structural assessment of steel in particular, and looking at the residual stresses and strains that can lead to failures in steel and welds. And so it's used to inform materials development and weld optimization in particular, and is quite heavily used by industry in Australia. And what we try to prevent with the use of highly penetrating neutrons is to prevent fracture, fatigue, distortion, such as you can see here on the left-hand side, and corrosion cracking, and inform industry how to improve the quality of their materials or resolve issues in their production process. So before I move on, because I'm going to be talking about CT scanning so much, I just want to make sure that we're all on the same page in terms of understanding the capabilities. So we have three modes of visualization here. On the left-hand side, when we're looking at a photograph of an object, we're looking at the scattering of radiation off the surface of an object. So we're looking at the surface of an object in photography. With a radiograph, the radiation, whether it's X-rays, neutrons, or some other form of radiation, they penetrate through the material. And so you get a two-dimensional image, which just shows you the shadow radiograph. When you're doing tomography, you need to move the radiation source relative to the object and collect hundreds or even thousands of radiographs, and from that use computation to generate a three-dimensional view of the inside of the material. So tomography is looking inside the object, radiography is looking through the object, and photography you're looking at the surface of an object. Now, the reason why I'm talking neutrons is because neutrons complement X-rays. The interaction between the atoms and neutrons is totally different compared to what happens with X-rays. So in the top image, neutrons are interacting with the nucleus of atoms, and because whereas X-rays interact with the electron cloud around each atom. And so what that means is we have totally different physical and quantum properties dictating the absorption and scattering of these different radiation sources. So a nice example of showing that difference is by these showing these radiographs of this camera. So if you look at the top image, neutrons interact quite strongly with light elements such as lithium and carbon and hydrogen. And so on the top image, on the left-hand side, the lithium-ion battery shows up quite dark, quite well, whereas it's invisible to the X-rays on the lower image because low Z materials contain very few electrons, so they don't scatter X-rays strongly. The lens shows up dark in both because the lens contains gadolinium in this case, and gadolinium is both a strong X-ray and neutron absorber. Also notice the film on the top right side is visible with neutrons and invisible with X-rays. So overall, you tend to have better penetration for steels and most metals with neutrons relative to X-rays, and you see different things, they're complementary. To put that another way, if you look at the attenuation coefficient, when you go to the doctor and get an X-ray, those X-rays pass through your light materials, your carbon, hydrogen, your soft tissue, but stop by calcium in your body. And what you see here is that as you progress down the periodic table, the stopping power increases for X-rays. Whereas with neutrons, because it's a nuclear spin interaction, you see a more random effect. So here you see boron, for example, is a very strong neutron absorber, whereas lead is very transparent to neutrons. Now, this unique property of neutrons means that we have a very large and diverse user base. So looking at the utilization of our instrument, it really follows the interests of our instrument scientist team as well. So about half of what we do is engagement with museums, either through cultural heritage or paleontology. And the majority of the rest of what we do is geology, earth sciences, engineering, condensed matter physics, representing the strength, in this case, of Ulf and his high pressure equipment and other really cool methods that he's developing. So in summary, users come to us to use neutron imaging to look at flow of water, condensation of moisture, for example, in fuel cells. We'll look at, again, moisture in soils and plants. We'll look at porosity in metals such as titanium and other engineered components, CT scan meteorites from space, and even do some radiobiology. Now, my talk is on heritage, and I've deliberately left the word cultural out because cultural heritage and heritage actually includes paleontology according to the definition of UNESCO. And my start in this field, my introduction, actually came through outreach. So Christine mentioned earlier that I used to manage access to ANSTO's nuclear facilities. I used to manage our user office. And it was in that role in 2015 that I actually attended the National Youth Science Forum in Canberra to engage with Year 11 students, so around 15 years old. And our neutron imaging instrument was being built. And I as part of my presentation, I spoke about all the exciting instrumentation that we're building at our new reactor then, and the fact that I was interested in actually conducting dinosaur research. And just one student in the audience actually jumped up with so much excitement, announcing that he was actually a volunteer at the Australian Age of Dinosaurs Museum. And so even before I intended to reach out to museums, this student actually put me in direct contact with the managing director and founder of the museum, David Elliott. David Elliott was a sheep farmer who found fossils in his farm in central Queensland, and one thing led to another, and now he operates a very successful and very large museum in central Queensland, and it's really the centre of dinosaurs discovery in Australia at the moment. And our discussion with David was the same as most other museums in that they were hesitant to even consider the use of nuclear methods because of the concerns about residual radioactivity. Can you put a dinosaur in a nuclear reactor and then return it safely? And so as part of that questions, he sent us our first test samples. And these are little nodules that are found in on the desert floor. And these represent marine depositions. Inside them, you've got fossils. And so the first question was, can we see what X-rays can't see? And so the very first image we got in paleontology on our instrument was this really beautiful image of a fossil crab in a rock that lived 112 million years ago. And the contrast that we're seeing here is actually seeing the chitin, the organic remains. We're seeing the scattering of neutrons by hydrogen within the nodule, providing unique contrast. And this is really important to the museums because it means that they don't need to crack open these nodules to work out which orientation these probes of fossils are in, whether they're complete and whether they're worth preparing. And so based on this information, museums can save hundreds of hours of physical preparation time, and they can take these neutron images and then they can use that as guidance to physically prepare and display these fossils, such as are shown in the museum here. Now, Christine mentioned that I also use X-rays. So down at the Australian Synchrotron, we have two imaging beamlines, the imaging medical beamline for imaging large objects. And here I've got Australorvanita. This is the leg bone of Australia's largest meat-eating dinosaur on the right-hand side, and the skull of Psittacosaurus from China on the left-hand side. I do a lot of that imaging there, but quite often we need to use both neutrons and X-rays as complements to get a holistic visualization of what's happening inside. Now, by far the most successful project we've had was actually the study of these amphibians and reptiles from Oklahoma in the USA. So they come from a cave deposit, they're Permian, and we're collaborating with Professor Robert Rice at the University of Toronto. And these specimens are quite cool. The bones are black because they are deposited in a calcite, in a limestone cave system. Underneath that cave system is a petroleum deposit, and that petroleum has infiltrated these bones that actually smell like oil. And hydrogen scatters neutrons, and this hydrogen, this petroleum, actually provides exceptional contrast. It's a contrast agent for us. And it was through these fossils that I really understood the benefit of neutron imaging to the paleontology community. It was hard to sell neutrons to paleontologists because we didn't know what the sales pitch was. And it's quite simple. One, neutrons can see hydrogen in rocks. So that means we can see soft tissue. We can see organic remains. And two, neutrons can penetrate through iron-rich materials. So in this case, when we image this skull with neutrons, we get no interference from all the fool's gold, the pyrite that's in the fossil. But if you do the same radiograph using X-rays, at a synchrotron, for example, you see all these black spots, and each of those black spots is this fool's gold. Now, the issue with that is when you do your CT reconstruction and look at your slices through your fossil, you see pyrite masses show up as bright white mess in your X-rays, and they hinder the resolving of the bones. The bones are actually invisible. Whereas in this case, when you scan with neutrons, the pyrite is transparent, and the hydrogen from the petroleum is showing those bones up beautifully. So we can actually distinguish what is bone and what is matrix, and that's very special. In fact, the resolving power of neutrons in this case is so exceptional that when we look at these cross-sections of these fossils, it's like they died yesterday. It's like a human being has gone to a medical facility and got an X-ray scan. We can see individual parts of bones. We can look at the internal structure and find out last meals and so on. With neutrons, I get asked, what's our penetrating ability? What I'm showing you here is a block that's 20 by 20 centimeters. It's basically a 20 centimeter cube block, and it's a death array, a death assemblage. Neutrons are very quickly able to scan through this large, massive, multi-kilogram block, and we can then digitally excavate those fossils, and from that make these discoveries. And one of the discoveries we made from this block was the oldest known fossil reptile skin in the world, and that was announced about 2 years ago or so. Now, I mentioned iron-rich material. That's really important. In Australia, we have huge amounts of ironstone. We're known for it. We export it. And in the Winton Formation, a lot of the fossils are found in these large iron-rich nodules. And in this case, I actually had to combine both neutron and synchrotron imaging over a 5-year program to convert this giant-looking chicken nugget to reveal what was inside. In this case, we found a crocodile that lived around 100 million years ago. And inside its stomach, all these little red bones here, we discovered something very special. And I've 3D printed them here to show you what they are. This tiny little bone here with a hook on it is actually a femur that belonged to an ornithopod dinosaur. What's special is that it's got a little bite mark here. The end of the bone is bitten off, and it was found within the stomach of this crocodile. And so one of the joys of working in this field is actually we get to work with paleo artists, and we get to translate our research discoveries into these beautiful life reconstructions, which then get worldwide attention. So in this case, we found the first evidence that crocodiles ate dinosaurs. We found a new species of dinosaur in a crocodile that lived 100 million years ago, which is really awesome. And in terms of other discoveries, our sensitivity to hydrogen and residual organic remains. Here is a mess, which was a fossil fish from the Gogo Formation in Australia. And you really can't see by eye unless you know what you're looking at. But this is stomach content here. There are other organic stomach remains and so on. But neutrons revealed this little red blob, which is a fossilized heart. And this is from a shark that lived around 400 million years ago. And this was published in Science in 2022 as the world's oldest fossil heart. And we were able to show even the inner chambers of this heart and how even by that time in evolutionary point, sharks' hearts had evolved to be similar to human hearts already. Sometimes neutrons stop us publishing work. In this case, we received a specimen from Jilin University, and they're very excited about a potential for a new dinosaur species here. It looks like a bird, it's not, it's actually a feathered dinosaur. But neutrons revealed a huge amount of adhesive or glue under the head, which raised suspicion that potentially this had been repaired or it was fraudulent. And so we actually had to retract the paper in this case before it was published, because using X-rays as further evidence, we're able to show that the skull of this bird dinosaur had been glued on from another specimen. So we had to go back and revise our research before publication. And now we're working on this specimen for other reasons. And so the primary benefit of neutrons to this field is that neutrons can penetrate through steel and iron-rich materials, have sensitivity to hydrogen and water. The only problem is people need to bring their samples to us. They're temporarily radioactive, but we can actually use that to our advantage. And so that was my introduction to the field of cultural heritage and paleontology through this student, and building up reputation through small museums, which then led to larger and larger collaborations. Moving on to cultural heritage. ANSTO has a unique research project, a research program focused on cultural heritage, actually, and we offer a wide range of unique nuclear beam techniques that are used to look at the structure and dynamics of materials, like I said, from the atomic to the macro scale. And these powerful tools can be used in tandem to extract information that answer long-standing conservational and curatorial questions for museums. And here I've got Floriano working with an Egyptian sample from the Australian Institute of Archaeology here. And Floriano and Ulf and my international colleagues use our neutron imaging and radiocarbon and other nuclear methods to look at the identification of ancient manufacturing technology, to assess conservation status, and to look at past interventions. You know, how were objects restored in the past, and how can we preserve them for future generations? So just to highlight one student and the potential work that one student can achieve over the life of their PhD, I introduce here Carla Raymond, who was a PhD student of ours from Macquarie University. So she worked with the Australian Institute of Archaeology and Macquarie Medical Imaging Facility and us to look at the Egyptian specimens that we have in Australia. And in 2019, she actually published the first ever neutron imaging scan conducted on Egyptian mummified remains. And this was of a mummified cat, or the scans revealed half a cat. And in this case, radiocarbon dating of the internal remains and the external wrappings was used to demonstrate that both were ancient, but the wrappings were 500 years younger than the cat that was inside. And so we were able to show the first evidence that ancient Egyptians couldn't breed enough cats to sacrifice in their temples. And so after many years, they actually went back into those temples, unwrapped those cats, broke them apart, rewrapped them, and then re-offered them to temples as a renewable resource, I guess, which is quite fascinating. Another project that Carla worked on was showing that neutron imaging could look at repairs and previous conservation efforts for, in this case, a white ground lekuthos, which is a flask from ancient Greece. And when you scan this with X-rays, you get the image on the left-hand side. You can see all these cracks, but you have no information about which adhesives were used and whether any other binding agents were holding this together. And yet when you scan it with neutrons, in the radiograph alone, you show that any repairs, so if you've got clay mixed with adhesive, it shows up brightly. And we can even see the sticky tape that was used to hold together the internal parts as this was being rebuilt. And that's totally impossible with any other method. So it gives you new insights into past repairs. I've mentioned earlier that neutrons can image through lead, and Carla demonstrated that in CT scanning an ancient Roman lead anchor. And in this case, was actually able to visualize the wood that was used as the template before the lead was poured. And this immediately revealed the mechanism by which these Roman lead anchors were manufactured, which was quite exciting. Now, I mentioned all of these studies, they take time. A typical neutron CT scan at this stage took about a day to 2 days. And so because we do a lot of work at the Australian synchrotron, where imaging is fast and happens in scales of minutes, we decided to attempt replicating the scan process, continuous rotation of objects, just like synchrotrons do. And we're not the first facility to do this. Other facilities were doing it, but it took us a lot of mechanical and engineering modifications to enable it. And that meant that we're able to achieve the same essentially quality scans for cultural heritage applications. Instead of 1 day, we could achieve those scans in 20 minutes. And in this case, this is with an effective voxel size of about 26 microns. So we can see all the writing on these ancient clay tablets here. So the first application of that was actually with a neutron school. One of the students called up and says, "Can I bring some samples?" And they brought what they believe were potential indigenous, First Nations artifacts, but they weren't sure. And in fact, because we could do this high throughput scanning method, we scanned about 50 of these rocks and were able to digitally delete the coral that was on the outside of them and demonstrate without a doubt that these were ancient First Nations tools. And these were from an underwater deposit in far north Australia. And in fact, provide the evidence for the first underwater Aboriginal deposit in Australia, which is very exciting and is now leading for a push for conservation status of that area. Now that brings us to the Invisible Revealed. The Invisible Revealed is actually the world's first major public exhibition of nuclear methods, in particular neutron imaging, applied to a cultural heritage collection. And this is at the Powerhouse Museum, which is at Australia's largest cultural and technical museum, located in Sydney. If you haven't heard of the Powerhouse Museum, or if you haven't come to Sydney, it's undergoing renovations at the moment, so it's closed. The main campus is based right next to the CBD, the centre of the city. But they're also building this new very large museum in central Sydney, a place called Parramatta, and they've got a number of other campuses as well. And our first engagement with the museum was actually through fossils. In this case, we had this Baenotherium, this early stem mammal from China. When you try to scan this fossil with X-rays, all the rare earths and the heavy metals make it impossible to see. And yet when we scan this with neutrons, it reveals soft tissue remains. There's a fossilized brain, not a brain cast, but the actual brain itself. Tooth replacement, there's muscles, a fossilized eye, and all sorts of other really cool things in there. This remains to be published. But at that time, the museum had a 3D printing exhibition on and asked us to submit an object. And in this case, we turned this fossil into a three-dimensional jigsaw puzzle, which went on display in the museum, which was called the Museum of Applied Arts at that time. So learning about our engagement with Carla and other students, the high throughput neutron imaging methods, and the trust that we had built with museums, the Powerhouse Museum came to us with a concept. And this is right before COVID. So they said, we would love to do a major exhibition that showcases nuclear methods and how they can be applied to conserve our objects for future generations. Can we collaborate? And of course, as a government facility who crave outreach opportunities, we said, absolutely. Now, you may question, how do you engage with museums? Well, it's very important to make sure that you're on the same page. And so we sat down with the museum, and they put forward a proposal to us on a number of objects from their collection that had these curatorial and conservation questions. And so they had a portfolio of about 50 objects such as this. Here, there's a conservation research statement, and they wanted to know what synthetic dyes, in this case, was this object colored with. And so we'd go through each of the objects and work out were nuclear methods applicable, and if not, where could we send that object for research. So from that portfolio, we then came to an agreement on a number of objects that were possible to image in our case during COVID, when most of our facilities were not accessible. And so we put in a formal submission that explained what the potential exhibition was, why they needed rapid neutron imaging in this case, and what all the details were around about the specific objects. Ultimately, 45 objects came to our nuclear facility. We used 9 different nuclear and synchrotron methods listed here over a 6-month period to investigate these objects. And this was our in-kind contribution to this museum exhibition. And so about 20 staff were involved from across ANSTO's campuses. I was the lead from the ANSTO for this. And I just emphasized this was hard lockdown COVID research. So what that meant is there was no face-to-face engagement with museum staff at all. In this case, delivery of specimens arrived in May 2021, and the truck just dropped this huge crate off at the entrance of ANSTO, and then I had to trolley this in. It was a very strange environment to be working in, but it meant that during COVID, I was able to do some lab work. And to highlight some of the things that we achieved with the museum, just the first example, this was a policeman's spy camera watch from the early 1900s. And the museum wanted to understand how it operated. And so this is the first sample we put in the beam. We collected a single radiograph and immediately panicked and turned the beam off. And the reason for that is we discovered with neutrons that the original film was still in the canister. Now, if we'd scanned this with X-rays, we wouldn't have seen that film. And the risk of exposure by X-rays is much higher than with neutrons. Neutrons are so gentle that there's a chance that that photographic film that might have crime scene evidence has not been altered in any way. We don't know that because the museum hasn't decided what to do with it, but it's a really cool case just to show that what we can see in simple objects. The museum brought to us an Enigma machine, a German cipher machine, and it was too large at that time for us to rotate and CT scan. But as part of the exhibition, we collected a number of radiographs just to show what neutrons could see. And we have a current project to actually CT scan this so we can digitally deconstruct this coding machine and see if we can digitally decode it without opening it. And that's a potential student project. But it just shows neutrons here can penetrate through plastics, the bakelite, the steel, the copper, and so forth, and get a full image of this beautiful machine. The museum, working with the museums comes with challenges. In this case, we've got Tang Dynasty horse. This is the largest object that's ever been in our neutron imaging instrument. And it was about 65 centimeters wide, 45 centimeters tall. And we did radiography on this. And here in the museum, we've actually got a full-scale radiography printed behind the horse. So this is the entrance to the exhibit. And I just want to highlight here that the neutrons highlighting in black any regions where adhesives have been used to repair the horse in the past. So we're seeing part of the ear has been replaced. Down here in the ankle, there's been a repair as well. And based on this information, the museum was actually worked out that this horse should not be transported interstate for an exhibit, so it stayed in Sydney. Now, the University of New South Wales was a partner in this exhibition, and they collaborated through the Epicentre, which is the Expanded Perception and Interaction Centre. So they actually created 3D models of a number of the samples that we were working with. In this case, they did photogrammetry on this horse. They developed new AI methods for generating these 3D renders. And we worked with the museum staff and the university to integrate our engineering drawings, the models of the samples, and to create a digital twin, which is a full-blown digital environment that represents our facility. Now, you've got to remember, we're in a lab that's in the base of a nuclear reactor. It's not accessible to the public. So how do you present to the public how our instrument operates? And while you see this as a video, this was actually a fully three-dimensional immersive environment that, in this case, explains the process of neutron imaging and how the particles interact with those objects, penetrate through the object where they hit a scintillator to generate an image, which is then stitched together on a camera. So this digital twin was available and presented during the museum exhibition for public consumption as well. I'll let this finish. So this just shows our scientific camera, and the outputs of that camera are these 20 by 20 centimeter grids, which are the portions of the horse, and that goes through the process of showing how we stitch the objects together and how we digitally remove the plinth for the final museum exhibition. And I'll just let that run there. I find these are a really elegant way of demonstrating how a method works to members of the public who really struggle to understand what we do. Tomography. So a number of objects were CT scanned. In this case, this is an ancient Greek statue. And the question here was, were there any residual organic remains? Beeswax was used as a binding agent in ancient Greece. So pigment was mixed with beeswax that was applied to the surface of this limestone statue. And we're used to seeing Greek marble statues as all white, but they were actually vividly colored. And so in this case, the museum wanted to know what were the original colors of this statue. Could they confirm that using XRF and other methods? And could they extract the beeswax and use that to date the object? And neutron scans are very sensitive to hydrogen. And so we're very easily able to show in a matter of minutes where any residual beeswax was. And some of those were sampled, radiocarbon dated to confirm the object was from around 500 BCE. And that pigment blended in with this beeswax was red. So we knew that Artemis in this case was wearing a red robe. And here is the object on display in the museum next to the neutron scan and an explanation, which is very small here, you can't see. So we were challenged with objects. The Curta calculator here is the world's first handheld mechanical calculator and provided a challenge for the museum and us. People know what they look like, but they wanted us to demonstrate the inner workings of this object. When they tried to scan this with X-rays, they got no contrast between the different metal components, which made it a bit of a challenge. But placing this in the neutron beam, we got exceptional contrast between the different alloys and metals used in the construction of this device. And two 20-minute scans enabled us to produce this beautiful render, which was exhibited at the museum. So again, each of the colors that you're seeing there is a different metal that was used in the construction. And you're even seeing a little sticker down on the bottom there as well. Neutrons can penetrate through gold, far better penetration than X-rays. And so the museum had in its collection this musical watch that was no longer functional, and they didn't know how to open it, so they didn't know what it contained. And the first radiograph from neutrons showed these bars along here. And straight away, we learned that this was a musical watch, an early 1800s musical watch. And we've rendered this CT scan. We now have an ongoing project with the museum to actually digitally reconstruct the sound of this watch from the structure and the known composition. And that's a project that we're working on at the moment. And here are these objects on display in the museum where we had neutron imaging out on display for the public, which was fantastic. Now onto synchrotron. So flat objects are not ideal CT scan objects. The ideal shape for synchrotron or any tomography is actually a cylinder. Humans are approximately a cylinder, so we scan quite well. But the museum had in its collection this lazarclave or clavus, which is a 1 meter long piece of fabric. And this was worn over the shoulder, and in Roman times was used to signify office. Senators would wear these as a sign of rank. And these later became adopted as fashion statements in Greco-Roman Egypt. So members of the public wore these. Now, the concept was that we wanted to scan this fabric at the highest possible resolution at our synchrotron to reveal the individual fibers and look at the direction of the fibers to work out how this fabric had been manufactured, whether any repairs had been done at the moment, and just to show the absolute technical limits of what we could achieve at ANSTO. Now, because flat objects aren't ideal for CT scanning, it enabled us to show a new capability for us, which was laminography, where you basically just tilt the object relative to the incoming beam, and that enhances resolution in a plane. And so based on that, and my colleagues in Melbourne, this is COVID, so we couldn't cross borders. So they did this scan for us. 1.5 terabytes of data enabled a full reconstruction of this cloth. Now, if you were to print this at full scale, which is 31,000 pixels, you could line the walls of an art gallery 6 meters long with this CT scan, just to give you an idea of the resolving power. And in this case, we're able to zoom in, look at a single section that had been repaired, zoom in again, and look at every single fiber. Now, the challenge for us is, how did we represent that in the museum context? Well, it's very difficult to do the imaging and the segmentation that they wanted us to do to show all the alignment during COVID when I had to work on a laptop. So ultimately, we decided to, if you've seen Star Wars, when Luke Skywalker is traveling over the Death Star at very low altitude and about to drop the bombs, you could see we've done that kind of trail. So we had a little digital camera, like a synthetic camera, run over the surface of the fabric to give you a feel for the roughness of it as you glided over it. And that's how we presented that in the museum. And they absolutely love that. Next to it was a case where an ancient Urtuk fabric was scanned, and then artificial intelligence was used to fill in the gaps. And where you can see it's gray is a video scan that's running through that fabric at the moment that's replacing the black areas with gray and then infilling it with color, just showing one of the new capabilities at the University of New South Wales. What was fun for us was actually the opportunity to show how we can merge neutrons with other methods. And so Floriana worked on an authentication study of a Shang Dynasty bronze vessel with the museum. Previous attempts to X-ray it, this is what they got. This is the best X-rays could do at the time. Whereas with neutrons, a simple CT scan, you can measure the wall thickness, the corrosion, the mineralization. You could see the past restoration. And then we could couple that with particle-induced X-ray emission, PIXI, to actually look chemically at the corrosion layer. So coupling neutron imaging with corrosion studies directly to look at the chemistry and understand how this jewelry, this wine vessel, was corroding over time and how that corrosion could be halted. And that object was on display here in the museum. Another thing that we were interested in showing was when you do CT scans are grayscale. So it makes it very hard to differentiate different materials and to identify them. But if you do multimodal neutron and X-ray imaging, which is now available at multiple facilities around the world, such as at the ILL and at the Paul Scherrer Institute and others, if you scan an object 3 times, if you scan it with neutrons and you color code that grayscale CT scan, you define that as red, and then you get a second scan, in this case with the monochromatic X-rays, and allocate that green, and you get a third scan under a different setting and allocate that blue. When you merge those red, green, blue scans, you then get a false color image where you can very easily identify different materials based on the joint attenuation differences of neutrons and different energy X-rays. And so that means that for large-scale objects, you can actually do material identification without opening the object. In this case, the camera has 3 lenses. 1, 2, 3. 2 of them are pink, 1 is blue. So the one in the middle is a different composition to the ones on the outside. And this was represented for the first time in the museum to show this new capability, which was really exciting. This was applied to statues as well. Here we're showing that X-rays show the lead glaze and neutrons show the repairs, sorry, the other way around, red and neutrons, blue is X-rays, and we could merge those to generate a composite image, which was informative. Moving on, not everything's about imaging. Neutron diffraction was used. Just to keep it simple, if you send a neutron beam or an X-ray beam at a repeating unit like a crystalline material, you diffract or scatter those beams in a way that produces these spike patterns, and those spike patterns can be studied on echidna to determine the phase, the composition of materials. That's for a non-stressed material. For a piece of metal that's bent or been manufactured in any way, when you pass those neutrons through that stressed material, the direction of travel of those X-rays or neutrons will change. And based on that change, you can actually measure the displacement of atoms relative to their normal position. And so Kawari, our residual stress strainer, is actually used to study massive pipes and other typically impenetrable steels and measure the stresses along welds to inform weld technologies. In our case, in cultural heritage, we can use these same methods to work out, in this case, these Cypriot copper daggers, so they predate the Bronze Age. Many of these daggers are found bent. And so the natural question is, were these manufactured deliberately bent, or were they bent at the grave site? So were they bent at high or low temperature? And using Kawari, we can measure the residual stresses in different components in different directions. So we get this red curve and this blue curve. They're meaningless without having a reference. And so if you look at modern day materials, if you compare this red curve on the left to this red curve on the right, the red curve on the right is a transverse component residual stress in a profile of a hot rolled copper strip. So that tells us that this copper dagger was hot rolled, just like this modern strip. On the right-hand side, this blue curve here matches this blue curve here, and this is a residual stress of a cold bent aluminium plate. So based on this data, we now know that this ancient copper dagger was hot rolled and then cold bent. And that was really exciting for the museum and a new discovery for us. Now, metals are made up of different crystals, and those crystals are aligned relative to each other or randomly, typically, unless the object has been rolled or manufactured or hammered in some way. And so we can use Kawari to measure the texture or the crystallographic orientation of crystals in materials. We can do that on 2 of our instruments, Kawari and Wombat. And here, this is what data looks like if there's no preferred orientation, if there's been no compression or loading on the sample. But if you hammer it or roll it in some way, you get preferred alignment of the crystals, like you can see here, they're squished. And so Floriana has been using this method at ANSTO to look at ancient coins and modern ones, and look at methods that we use to manufacture these coins, and whether they're cold hammered, hot forged, or cast based on the texture information. And that's quite important for historical manufacturing method studies. So in the museum context, at the Powerhouse Museum, this same method was applied to these samurai swords from the Powerhouse collection. So Floriana and colleagues, we're stuck, here we are, used a combination of neutron tomography to look at the cross-sections to identify the different steels used, verified using diffraction, and diffraction peaks differ depending on what style was used, and these are often layered metals, and then using residual stress to identify the manufacturing method. So using a combination of these nuclear methods, we're able to visualize what the material is made out of, the variation in space, and then the manufacturing method. And then traveling to other neutron facilities, in this case in Japan, able to look at the texture of the sword to verify that manufacturing method. And these were displayed. In fact, we learned after the exhibit that the swords should have been displayed upside down relative to what we had. This is how they were displayed, which was culturally incorrect. The museum had in its collection a coin that it believed to be fraudulent, a fake coin, and they purchased it at auction, believing it was a potential forgery. And so they posed this as a problem, knowing that we could image through gold, and wanted to know this Lydian stater is officially the first coin manufactured by a government around 600 BC. And the question was this fraudulent or was this a genuine coin? And the way we can tell that is because fraudulent coins typically made of tungsten because it has roughly the same density as gold, and they're clad in gold. So this coin was brought to our lab. A rapid CT scan verified that the coin was in fact solid, that the internal corrosion was consistent with long-term corrosion as opposed to a rapid modern manufacturing process. And in this case, the fact that neutrons activated the coin made it radioactive meant that we could conduct neutron activation analysis, so we could measure the gamma rays emitted by the temporarily radioactive coin. And from that, we were able to verify its elemental composition, that it was predominantly gold with a small amount of silver and other elements present. In other words, this was a genuine gold coin. So based on the neutron scans, the neutron activation analysis, plus numismatic study by Professor Ken Sheedy, he was able to, you don't need to read through this, but if you watch a recording, you can pause it. But in summary, we're very excited because not only is this a Lydian coin, but it's actually a second generation Lydian coin from the fall of the empire. And there are only four known examples in the world. And so the museum now has in its collection an extremely rare coin from a very particular point in time of the Lydian Empire. There was a large program of research with our First Nations collaborators at the museum. And one of the objects was a potential women's object. That came with unique challenges for us. That meant that as a man, I was unable to lay eyes on this object without at all. No permission could be granted. And so this ceremonial knife was brought to us in a box and CT scanned in the box with none of us putting eyes on the object. And it was only upon digital reconstruction of the knife, which I was allowed to do, that I went through the process of deconstructing it to look inside it. Number one, that was culturally insensitive. I learnt from that experience that even a digital separation of materials is inconsistent with First Nations practice in this part of Australia. And so when you're consulting with the Indigenous communities, it's really important to understand the cultural context of the objects that you're working with so that you can work with it with respect. It was fine in the end, but it was a really good education process. So in this case, synchrotron imaging revealed that the seeds on the outside were averil seeds, that the blade was made of cassowary bone, and the hilt was made of wax. And by looking at the internals, we were able to verify that this was not a women's object, and therefore I could lay eyes on it, and the museum could exhibit the results of the scan along with the object. The museum also had in its possession the oldest known boomerang from the state of New South Wales, from Sydney. And so this was radiocarbon dated. And Tammy Gisso, who's the Powerhouse Museum First Nations coordinator, came with us with a series of questions wanting to know what technologies were used to manufacture this boomerang. Was it made of local wood or had it been traded locally? And this is an ongoing investigation. So these objects were displayed in the museum next to each other with the CT scans behind. Ultimately, 26 of the 45 objects we worked on were displayed, representing 3,000 years of human development, 9 nuclear methods, and the exhibition was really successful. It was initially planned for November 2021 to March 2022. It was extended to May, and then it was further extended to September. So when Australians came out of COVID lockdown in Sydney, this was the first exhibit that was on at the museum. This is a walkthrough of the exhibit here. The museum staff worked with us to create a scientific glossary to explain the nuclear methods that have been applied for each of the objects, and this is available online. There are a number of live events. So there was a First Nations interpretive dance, public lectures and tours and so forth that went along with the exhibit. Visitors to the museum could take out their mobile phones and take photos of the QR codes, and they could take the photogrammetry or the CT scan and of this statue in this case and take it home with them, so they could have this augmented reality object at home with them for study. Further, the museum has publicly declared that it's got a number of objects in its collection of incomplete provenance. They have not verified where these objects come from. And so neutron imaging and other methods were used to analyze these objects. And on the Powerhouse Museum website, they actually include examples of our outputs, our data that we've generated, with a call out seeking information about the provenance of these objects so that they can be either repatriated or maintained with permission. And so based on the innovations that were put together in this museum exhibition, we're actually awarded the Museum and Galleries National Award for Research in 2022, which is a really prestigious thing and quite exciting for the first public nuclear exhibition in Australia. So if any of you are interested in working with museums, it's important that you prepare for the risks that are associated with working with cultural heritage. So to create a risk register, to develop a policy and procedures for handling cultural objects, what happens if you identify if something is stolen, for example. We have had to repatriate fossils in the past. We've had that experience. But the most important thing is whoever you work with, you respect collaboratively, whether it's in the field or back in the labs. ANSTO is working very hard in developing a reconciliation action plan. So this is a plan for our scientists and staff to work collaboratively with our First Nations representatives. And we publicly declare all research that we do with First Nations people or Indigenous material across the country. I'll just highlight that according to UNESCO, fossils are considered cultural property, and so it's very important that they come with documentation, otherwise they can be seized by customs. And in fact, there's a court case beginning today, I believe, in Western Australia about people who are fossicking in an area that they shouldn't have been. So as a facility, we request documentation. So that might be an object loan agreement to show that the person visiting our facility has permission to hold that object. And also we request biosecurity letters stating the object is clean and free of any biosecurity material. So that might be dirt or worms and things like that. So based on this aggregated experience that we've acquired at our labs, we've actually communicated with the IAEA, the International Atomic Energy Agency. We've had a collaborating center for many years, and we provide consultation with the IAEA and have made numerous visits to Vienna as a team to discuss how we can use nuclear methods to contribute to the fight of the illicit trafficking in cultural property. Now, lastly, working with museums gives us a real opportunity to sort of infiltrate nuclear methods into the public without people realizing and showcasing what we do. So it's fun. Every time I travel around the world, we visit museums. In this case, the Danish Natural History Museum. As soon as you're walking to the museum, right there in the corner, there's a 3D print of a pterodactyl, or a pterosaur, I should say, that was generated using neutron and synchrotron imaging data from our facility. You go more locally to our local universities, and our work on that lekithos, or an ancient rolled lead scroll or coins, the neutron data are actually on display with the objects. And this is a really important and effective means of reaching out to larger numbers of people. The Australian Age of Dinosaurs, there's that ancient crocodile. Above it is a television screen that highlights our neutron and synchrotron imaging data. But not everything needs to be on the large scale. We have an active program of public outreach where we will take real fossils out to schools and to scout groups and really excite these students about what we can do. We'll install massive public exhibitions of explaining, in this case, what paleontology and imaging and neutron imaging are to the community and put those on display in public libraries. But we've also managed to get our facility's first ever data in coinage and a postage stamp. So here is an example of a dinosaur, an Elaphrosaurine, that was discovered using our imaging processes. And the year that we published the paper, Australia Post and our Mint manufactured this coin and stamp to go along with the announcement of our paper and our research. And that actually came out as part of a larger collection. And we've actually worked with all of these specimens. And right now in the lab, we actually have a specimen of Australoveneta, which we're working on CT scanning right now. Where to from here? So because we developed these high throughput imaging methods and these other techniques for cultural heritage, they've led to innovations and realizations. So we have a very large mining industry here in Australia where X-rays are typically used for mineral identification. So the question is, why can't we do that with neutrons? Why can't we see through lead and gold deposits that you can't with X-rays? And the simple answer is you can, but we're just not fast enough. So this led to us inventing a parallelized CT scanning system where we can CT scan 2 or 3 1-meter long mining drill cores simultaneously with neutrons, speeding up the process of imaging. So now we can actually CT scan about 1 meter of drill core every half hour, which is as fast as you can do with X-rays. We're currently validating that process, verifying that neutrons support X-ray fluorescence data. X-ray fluorescence only gives you surface mapping. Neutrons gives you full 3D render, which potentially increases the accuracy of your reporting of your mine value. So we have a major collaboration, $1 million collaboration with James Cook University to develop this to a potential commercial product. The Paul Scherrer Institute in Switzerland donated their old neutron microscope to us. We've upgraded it, and Florian has produced the first paper on that case, looking at the Chiaraval cross, a 13th century masterpiece, in this case showcasing neutron imaging's capability and ability to look at welding between gold and silver at very high resolution, at 1 micron pixel size. The digital twin concept was great, but it didn't go to an actual practical digital twin that modeled our radiation field, our neutron, what energy neutrons do we have in our beam and so forth. And so our ANSTO Human Health team have been working with us over a number of years to develop a fully functioning digital model of our instrument. And the idea is that it can inform all research quality and develop new capabilities such as radiobiology research on our imaging instrument. Based on that, we finally measured for the first time our energy spectrum. And this is the energy of our neutrons. These are thermal neutrons, lower energy, faster epithermal neutrons and fast neutrons, and then the impact of using different filters on our beam. So we've now realized that we can use high and low pass filters, so we can do imaging with either low energy or high energy neutrons. Why is that important? It means that if someone comes to us with this drone fuel cell, for example, if we tried to CT scan this in the past, we couldn't penetrate through all the plastic. But if we place a sheet of cadmium in our beam and use the higher energy neutrons, all of a sudden we can resolve or image through that plastic and see the internal details for the first time. So all of these have actually led to new collaborations back with the Powerhouse Museum. So they're excited about our new capabilities. With the opening of their new museum in Parramatta, they're launching an exhibit called Task Eternal, which is about our human mission to fly and enter space. And so it goes from boomerangs through to astronaut spacesuits. And as part of that, we're imaging and studying a number of objects. So you may not have heard of Lawrence Hargrave. He was an Australian aviation pioneer. In fact, the first person to actually fly, not with a hot air balloon, but with kites. He built a rotary engine. He invented the box kite. The Wright brothers' flying engine was actually based on his box kite design, and they used his rotary engine design as well. You may not have heard of him because he hadn't patented any of his designs. He offered them free to the world for study. Well, in the museum's collection, they've got the Lawrence Hargrave engine #1. And in this case, this was previously unachievable in terms of neutron imaging because we could not penetrate through that much wood and so forth. And now using this new higher energy neutron imaging setup, we can actually see the mechanics through the wood, and we've created stop motion animations of this and other objects in the museum collection. I've just highlighted one. And so the message here is that our collaborations are expanding. Now, in 2023, Australian Research Council actually funded us $400,000 with the museum and the other universities for Nucleonation, a contemporary archaeology of Australia's atomic heritage. So the aim of this project is to actually write Australia's nuclear history and to look at the management of our heritage for future generations, which is really exciting and something that's totally different for us working on. So from our perspective, Our HIFAR, Australia's first nuclear reactor, is currently being decommissioned and dismantled. So the first thing we do, we got a photographer in there to capture the reactor as it was being dismantled. The control room is no longer in there. And so these are the last photographs from within the reactor before certain components were pulled out. And as part of that, we're looking forward to a new exhibition where we will be studying these tiles from buildings from Hiroshima and other objects from Australia's atomic history. And we'll be working towards a new exhibition focused on these objects in the future. Now, all this work is not just done solely, this is done with a huge number of collaborating scientists. So I thank in particular my colleagues at ANSTO, almost 100 staff across ANSTO and the Powerhouse Museum and the University of New South Wales for this museum exhibition, and many other collaborators that empowered me to actually change from a research admin career to a career in culture heritage and neutron imaging. To wrap up, if you want to learn more about neutron imaging, what capabilities are available locally to you at other facilities, the International Society for Neutron Radiography actually lists all accessible nuclear imaging facilities around the world. You're always free to reach out to me directly or to my teams, Dingo and Kawari. If you're interested in accessing our facilities, our deadline for merit access is 15th of March. So with that, I thank you for your time.
Thank you so much for this inspiring and exciting presentation. So, Joseph, it was really wonderful to see the broad as well capacity and the portfolio as well that you can reach, and as well to emphasize how to reveal this invisible thanks to our large research infrastructure with neutron capacity and photon. So thanks a lot for all of that. So we have a bit of time for questions. So thanks for everyone as well to have listened and to see indeed how we can potentially collaborate further and try to understand also from the perspective as well of your presentation, how future collaboration could be established. So we have first a basic question as well, just thinking also, or if you can summarize the source as well of the neutron beam for your reactor and potentially with spallation in very short ways. This is from Adam.
What was the question? Sorry, I just need to turn your volume up a little.
This is an early question that came, so while maybe you had not much presentation already given, but by Adam Jodowski, who was asking the source of the neutron beam.
Oh, right. Okay. So the two major sources for neutron beams are either spallation sources, where a target is hit with proton something and generates pulses of neutrons, or you have nuclear reactors that produce a constant stream of neutrons. And they come with their own benefits and challenges. So there are numerous nuclear reactors around the world, such as FRM2 in Munich, NCNR at NIST. There's HIFAR at Oak Ridge National Lab. There are reactors in Japan and so forth, many of them that have these high-powered constant neutron beams. And every single one of those facilities has imaging setups now, pretty much. And places like ILL and Grenoble have combined neutron X-ray stations where you can do both simultaneously. Now, the benefits of the spallation sources over the nuclear reactor sources are that the spallation sources allow you to do time of flight measurements, which means that you can do Bragg edge imaging. So you can do imaging that focuses on a specific element. So if you want to do elemental mapping, it's better to do that at a time of flight facility. If you purely want to generate as many CT scans as possible, it's typically best done at a nuclear reactor because you've got a high constant flux of neutrons. Now, the ESS is coming online very soon, where you've got the benefits of high flux and time of flight. And so I'm really excited to see what the opportunities are for collaboration with the ESS in particular, where you've got those overlapping pulses generating what's almost a continuous stream of neutrons, which again poses its own challenges for the team. So I wish you luck. But the challenges in paleontology are really the handling of the objects and culture heritage. You know, you can't cut these objects down. And even at our own synchrotron, you know, there's that mentality that you have limited motion controls in some of your instruments because you've got a high resolution setup. Therefore, all your samples are small. No, you may have a sample the size of your fist. and you want to do a very specific scan of a small region. The ESRF, that synchrotron, has a beautiful setup where you can do hierarchical scanning on large objects. Whether someone goes to a spallation source or a nuclear reactor or a synchrotron depends on the material composition and the resolution and the time frame they have for the study. I hope that's important too. And staff experience ultimately is why a lot of museums from around the world come to us, just because we have that experience, which I hope other facilities will gain over time.
Yeah, excellent summary. And indeed, the long pulse as well that we will have, so with the ESS, which I think is a great complement for not as well donating too much. So then we have a question by Malik Maza, so Professor Maza from South Africa as well, asking and speaking about the bone of the sample scan are calcium rich. So how active are the sample after such an exposure?
That's a really good question. So we've scanned maybe 2,000 or 3,000 fossils over the lifetime of our instrument so far. And typically, if we have iron-rich fossils, whether they're from, so we've received fossils from South Africa, from Tanzania, Australia, everywhere. Typically, if they're iron-rich, they're active for about 5 weeks. So after a 5-week period of staying locked up in our secure zone, they can be returned to the museums. Now, with the non-iron-rich samples, so the calcium carbonate, the limestone examples that I showed of the early reptiles and amphibians, they're typically active for 1 to 2 weeks only. So the longer-lived radioisotopes take longer to activate in the first place. So the faster you do the imaging, the less radioactive and the shorter the period of radioactivity of the objects. But we've had fossils where we do a half-day scan, they'll be white, so they'll be calcium-rich, no iron, and we've been able to clear them within a week and return. So some users can actually take them home at the end of their visits. Only in one instance did we have a real problem with a fossil, and that's because we didn't know that it contained naturally occurring uranium before we imaged it. And that taught us a very important lesson. So in that case, this was a tyrannosaur relative from Mongolia, and its ribs were very rich in uranium. And so when you expose uranium to neutrons, you generate neptunium and a small amount of plutonium signature. And we could detect these. And as a radioactive material, we could not give this specimen back. And so we developed very clear procedures now. So one, that object has gone back, and we held it for 3 months. And we use gamma spectroscopy to fully characterize those elements that were creating the radioactivity and demonstrated that was naturally occurring uranium. Based on that, we're actually able to get it cleared and returned home. And so now we have a process where we will temporarily, very briefly radioactivate all these objects and use a gamma spectrometer to get a feel for what elements are present. And we won't continue neutron scanning without doing that quick test. And so now that's a very important lesson. We always check for natural radioactivity before we put objects in the beam now. And so we've got fossils from Australia that are from caves that are active. We will write down on a form their naturally occurring radioactivity. And after imaging, once they return to their naturally radioactive level, they can be cleared to the lab. And that's unique. Most other places, if they detect radiation, you can't, then they stay home forever. And so that's an important lesson.
So a very rigorous protocol as well to be able to...
Yeah. The Egyptian remains, the one had a gold mask on it, so we had to hold that for 3 weeks. But biological material, sodium and calcium activate. Once they clear away, you can return the objects straight away. So some objects came to us, they went back the next day.
Very good. Thank you. So we have another question from Caridas Chapman, so asking and interested by, so how the insight from neutron CT compare to the MRI?
To MRI?
Yeah.
That's a good question. So we've only used MRI in a few instances, but MRI is not applicable where you've got iron-rich material. And so quite simply, we're getting internal insights that are impossible using MRI without some form of safety procedure in place. And so I'd say that the insights we're getting are unique from neutrons. That being said, there are MRIs being developed that can look within iron-rich objects now, but they're not really accessible to the public.
Yeah, good. And then also you mentioned that there was a lot of iron in the area where Australian fossil were deposited. So what is the reason behind this, and how can you potentially compare?
That's easy. Australia is this our continent is old, right? So we have cratons. We've got parts of the planet that are typically so that we've eroded down to bedrock that's not accessible in other parts of the planet. So we just have lots of iron. It's an old country. And so that iron becomes soluble in groundwater, and that groundwater flows into your fossils and impregnates them. And depending on the bacteria that are present at the time, it either oxidizes or reduces. So you either get iron pyrite, where the iron reacts with sulfur from the degrading biology, or you get these iron oxides building up. It's everywhere.
So the oldest dinosaur in the world would be also from Australia in some sense.
No,
The
I
oldest
wish.
ground.
We've actually CT scanned embryos of the oldest known dinosaurs from China, Lophosaurus, and found evidence of collagen in their bones, initially with neutrons and then using Raman spectroscopy to verify that. So no matter where you look, and that's something that's important to understand, the concept of fossilization that we're taught at school, that bones, organic material degrades, the bones dissolve and are replaced by minerals, is totally incorrect. You can actually go as far back in time as you look, and bone is still original bone. It's still calcium apatite. It's just modified with inclusions. Not always. And the mineralization process can actually encapsulate and preserve soft tissues. And so over time, we're finding things like blood vessels. We've seen them in our lab. You can extract collagen and other organics that you would never imagine would last geologic time.
Wonderful. So with also from Karina Sherman, her last question was also to see if there was any issue, so with unexpected element in artifact activating for a long period, so following the imaging.
We've had the opposite problem. So we've had issues where we've had mixed alloys of unknown composition. Typically, when you bring samples to a nuclear facility, you have to declare the elemental composition as part of the radiological assessment. We can't do that. And so, as I mentioned, we put objects in the beam for a short period of time to activate them and see what happens. There was one instance, we received a clock from Vienna, and we did that simple 5-minute exposure, and the clock was so radioactive, we could not enter the lab for 2 days. So in that instance, there was an element which we couldn't identify at the time, but it just stopped activity. And that clock was then active for 2 months, just based off a 5-minute radiograph. So from now, we actually only do a 2-second exposure first to check things. So there are some short-lived isotopes that cause problems. In terms of longer-lived ones, we haven't come across them yet.
What was the element
so slowly.
What was the element in the case of that clock?
We don't know. But to answer the question, if we do not irradiate objects with cobalt, for example, because we don't want to generate cobalt-60 with a half-life of 5.3 years. So if by accident we image something with cobalt in it, there's a good chance you won't get it back for about 20 years. So that's our one thing that we're really careful of, no cobalt in materials, please. Unless it's a mining sample and it can be disposed of and stored as nuclear wastes, as low-level waste for a period of time. We haven't come across that. It is an issue in super alloys in particular, new technologies, the high temperature materials can have a really interesting blend of nickel and other elements that can pose problems. But in that case, neutron imaging is the only technology that can be used to image the cracks or faults in some of these materials. And so it just has to be done.
Excellent. So we have another question also from Etam, Noah. So asking also if there is an international outreach program to perhaps have a traveling exhibition to showcase this research in various museums. So maybe this digital reconstruction way or tell us where to find that, and we can add the hyperlink as well somewhere.
I'll put it this way. The Powerhouse Museum was interested in having a traveling exhibit. And the only reason why they hadn't pursued it is because they've decanted the entire collection during this reconstruction phase of the museum. And so they were, I don't know now, but they were open to the option of traveling. They're actually having meetings about exhibiting it at our synchrotron in Melbourne, or collaborating with other nuclear facilities and museums so they can generate their own data to support their own exhibitions. So there is a nuclear methods and cultural heritage conference in Munich in May this year. And we will discuss exactly these questions. So hopefully that will come with solutions and future exhibitions. I know the Rijksmuseum is probably planning some form of exhibition based on nuclear methods. Anyway, we should talk and see what we can do with the ESS, for example.
Indeed, that would be wonderful to have across those different continents as well a showcase for that. So excellent. So we have one more question, so also from Alan, and I'll come back on the museum aspect later. Yeah, please.
Well, it's a follow-on to that comment. You know, when I was involved in the neutron facility community, that the issue for cultural heritage was funding. The government sources, at least in the U.S., were not interested. And so I also always felt that the outreach power of this work is so great that that private funding should be possible. Have you found that to be the case?
So we have found that all of this research is done on very small budgets, right? So at first, you know, the question is, why are we bothering to do cultural heritage? You know, that was questions from other scientists at our facility. What's the benefit? But then, and they're not counted, you know, if you do a museum exhibition, they're not counted as research publications and they're not counted as, you know, various things. And so they don't show up in certain metrics, but politicians love them. Members of the public see these exhibitions from industry, and it then raises questions in their minds about what can they do with these techniques. And so we have demonstrable outcomes from these outreach programs that have led to commercial utilization of our facilities, new utilization. So, you know, a simple exhibit has led to multiple commercial programs in mining industry, in medical programs. And so once you're able to demonstrate that link between, you know, you're scanning dinosaurs and cultural objects, and you can make people realize that's a feeder for other forms of engagement, then the support expands. And with the building reputation, you know, we've got numerous cultural heritage grants now, you know, of the $500,000 to $1 million scale. So they're even in a limited funding environment like in Australia, we are able to achieve grants to support our work because of the reputation and the experience that we've developed. But it does take 10 years to get to that point.
Yeah, very good. Very impressive.
And, you know, cultural heritage and First Nations programs, for example, and the ethics of conducting research are becoming more important over time. And so our perspective is cultural heritage work is just going to increase and there'll be more demand for it.
Well, if I may follow up on that, I always had the feeling that the indigenous talent pool was untapped in this area, at least in the U.S. And you're doing so much with the indigenous populations in Australia. Has that attracted the students into the field?
It has, relatively small number. But what it has attracted is investment in companies to authenticate food products. So in Australia, there's a fruit called a kakadu plum, for example, that is now grown both locally by indigenous populations, but it's also produced overseas. And so our First Nations people want to generate an income stream and protect their IP associated with the growth of these plums. And so ANSTO has been working with these communities and commercial companies to find ways to authenticate food origin. And this is a very big thing for us. It was on national TV just last week or the week before. And the same applies to prawns and others. So we're finding in that space where there's an opportunity for upsell and upmarket of of food products that can be validated using nuclear methods, that's sort of gaining traction with our communities here. We've attracted a small number of Indigenous students and new staff, which is exciting. But I'm just looking, I've actually got a paper here. There was a recent paper in the US, which is a really good example. Calvin So was from George Washington University, and they were studying these Triassic, doesn't matter what it is, there's monsoon Triassic things. But what I'm trying to highlight here is, in this case, the fossils were extracted from public land and preservations, not just with the permission of the preservation, the preservation office and the tribal leaders, but in direct collaboration with those leaders and the communities. And so in this example, the paper actually includes them as co-authors because they generally contributed to the research in ways that we could not do so. And we're starting to see that more and more, especially in paleontology, where there is permission granted to access the land. There's this diminishing colonial attitude to actually collaborate with locals and find out what the culture is and whether there is any cultural relationship between the material and the land and the people, and then integrating that in the research output. And I can provide examples of that.
Super.
Yeah, very nice. So thanks a lot for those details. And then also about museum, can you just explain a bit the process in terms of how one discovered bone as well will go from the hands of the scientists through the museum, and what are the different capacities as well for protecting and making sure that everything is not decayed further?
Oh, right. So you're asking what's the logistics?
Yes.
Chain of custody.
Yeah, exactly. So we have chain of custody documentation and procedures for nuclear materials. Every facility has those procedures in place, whether a spallation source or a nuclear reactor. All you need to do is take that documentation, replace the word nuclear with high value material, culture, heritage, whatever, and the same procedures apply. So for our system, every box is barcoded. The objects are handed over from one person to another. We have safes with keys, limited access rooms, and so forth. And depending on the value of the object, its rarity, and how precious it is, it either sits in a room, in a locker, or within the most secure place we have in our nuclear reactor, which is with our nuclear standards and other objects. And so it's very simple to ensure those protocols are in place. The greatest risk is actually at the point of the instrument, when an object needs to be placed on the instrument. There's risks of mechanical failure, collision. We've learnt the hard way that if you're rotating objects or moving them, you can either have direct drive mechanisms for your rotation stages, or you can have air bearings. If you've got air bearings and if something gets stuck, it stops. But if you've got a direct drive, then the machine will keep running at the risk of crushing the object. And so you've got to look at your mechanics of your instruments as well when handling these objects. And simple things like, in a lot of facilities, there's simply just a little gate that you can open and close to go into your instrument. We actually have interlocks, digital interlocks, that you need to press a button or a key to access the room. Things like that need to be implemented to handle these objects. You need to negotiate with the museums, whether it's the museum staff who are placing the objects on the instrument, loaning them to you, or maintaining possession, legal possession of those objects. And you also need to look at your insurance policies. So if you're signing object loan agreements, if those objects are coming to you and you are the loaning person, then unless your organization has those objects declared on their insurance policy, they're not covered. And so all these things need to be considered. So let's just say it's complicated, and the rules in every country are different. We have our procedures in place, but we can give you guidance on how to handle them. But it's a challenge.
Yeah, no commercialization of that yet. Of course. So then, while reading as well a bit in the chat box, so I saw as well that we had some comment and some question from Thomas Metzer. If you could also, if they can get a copy of some of the paleontology scan charts. So I guess that we will put the recording and the slides available for everyone, if it's okay?
Yes.
You,
Yes, of course. No problems.
on our page, but then as well some typical short or different scans. So I guess that you have the email at the end of your slide, and maybe
Yeah, so if anyone wants to reach out, if they want videos or other examples, so the ownership of the data is with the collaborators and with the museums. So as long as they grant permission, then I'm happy to distribute the actual CT scans or the reconstructions or whatever. So the answer is yes, just ask and we can find out what we can do.
very good. And indeed, we have so few of also of the audience, like Kate Ducan, who visited and confirmed that it's a
Yes.
wonderful exposition. So a colleague as well, I guess. And
Thank
also
you for
from
joining, Keith.
exactly, very good exposition, and I think everyone is fascinated. I can imagine. I've missed this still. But then with also the comment as well from Jeff Malonsky, who was speaking about at SNS, saying that they're excited to see what Venus can show them.
Absolutely. And I was there.
Can you describe a little bit? Yeah.
I visited Venus in December, and it was very exciting to see. They're already generating unbelievable results on large engineered infrastructure. So I'm aware they're already working with cultural heritage objects. I was in New York recently talking about the potential for neutron imaging and the museum. I can't for the life of me remember the name of the museum now because it's 3 a.m. here, 3:30. But they were keen to actually collaborate with Oak Ridge and deliver specimens there for scanning. So it looks like it will happen. And Venus is huge, right? So the field of view is large, the penetrating capability with the epithermal neutrons is high, the energy selectivity is great. So yeah, the only challenge is the low flux. So scanning takes time, but then they've developed AI methods to increase the speed at which they do these scans. So yeah.
Very good, very good. So go ahead.
So Keith asked a question, what are the thoughts on using neutron tomography for plant samples with respect to sample fixation? Good question. It depends on the, if you're referring to contrast agents, then the same rules would apply as with X-rays. It depends on the contrast agent that you're using. I can't answer any more than that because I'm not too familiar with the field. But ever since Kids Come, we've actually wanted to do more work in plant space, but our local universities haven't even explored that opportunity yet.
Thank you. Thanks a lot. So I think indeed this is the time right now. So to close this wonderful session. So time to wrap up, unfortunately, and to let you go to sleep. So this is almost more than 3:30 in the morning for you. So sorry for that, but thank you so much to share. You see, in time, the past, the future, everything is so little. So thanks a
Absolute
lot.
pleasure. Thank you very much for your time.
And thanks for everyone to have listened. And I will simply now, so thanks again, and share so my screen to present the next presentation. So next month, we'll finish as well this International Year of Quantum going to India. So that's going to be so with Professor Obasi Shinya, who will be presenting this quantum foundation to field deployment. So live this time from India. So it will be a pleasure to hear her and complete as well one earlier seminar that we had with her. And then in March, we'll go back as well to Ghana, where will be the ending as well of this International Year of Quantum. And we'll hear a bit more in terms of how physics as well can connect further with societal challenge more on the medical domain in that case. So thank you everyone for spending some time and to understand why physics matters. And I think we have the perfect example time-wise and space-wise, how and why this matters. So thanks a lot, Joseph, for your availability, and Alan and everyone for listening. And we'll stay tuned.
Bye-bye.
Thank you, everyone. And we have, a last question, but maybe we'll answer to Joe Paulo. So maybe just a little bit. So, so many thanks also. So just a small correction. The Australian synchrotron is the second brightest light source in the southern hemisphere, just behind the Brazilian light source, Sirius. So thank you.
Oh,
We were
Excellent. Good to know. Thank you.
Thank you so much, Johan.
very good.
and we had in our physics matter as well. So so Ari Westphal presenting the Cyrus star. So the second indeed now, but looking in the past, your reactor was the earliest. So thank you so much to everyone.
Pleasure. Take care. Bye.
Bye-bye.
Bye, everyone.